Today we'll be studying periodic law, looking at the periodic table, seeing how it's arranged, why it's arranged in that format, and identifying special groups and families. Be sure you have some color pencils or markers available so that you can label and color your periodic table. Organization is key. When you open your backpack, does it look like a trash can? Would you try to navigate the grocery store if everything was just randomly placed with no organization? This was the world of chemistry before the periodic table. Discoveries were slow, and scientists did not have a desire to delve in the field. By the mid-1800s, 70 elements had been discovered, but there was no attempt to compare similar features. When a task seems too hard to complete, nobody really wants to do it. And this was the world of chemistry. It wasn't very popular because there was no organization about the elements. It was too time-consuming to get anything accomplished, and nobody really wanted to deal with it. But then, along comes Dimitri Mendeleev, the father of the periodic table. He was a Russian chemist who listed the elements into vertical columns in order of increasing atomic mass. So in the back of your periodic table, let's write his name, Dimitri Mendeleev. And let's write two things about Dimitri Mendeleev. He organized the periodic table into vertical columns in order of increasing atomic mass. And we're not going to write this part down, but I do want to talk about it. He noticed a regular or periodic recurrence of physical and chemical properties. So he rearranged the columns so elements with similar properties were side by side. So let's write the second thing under Dimitri Mendeleev. The first is vertical columns in order of increasing atomic mass, and the second is similar properties were side by side. This led to the first periodic table. So as you went around the table, properties would repeat, hence the term periodic, which means to regularly repeat. So on his periodic table, just to make sure that we're very clear, on his periodic table, vertical columns, so column is top to bottom. So vertical columns, as you went from top to bottom, was increasing atomic mass. So atomic mass of 1 here, 2, 3, 4, increasing atomic mass from top to bottom. That meant that similar properties occurred side by side. So one example, and this isn't anything you'd actually see on the periodic table, but one example would be to put everything that was blue side by side. So blue, 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 blue side by side. And then the next row, everybody was all green, 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 green. And then the next row would be red, 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 red. So as you went through the periodic table and you read it from left to right or top to bottom, you'd see a periodic trend, or you'd see a regular repeating occurrence or pattern of properties. So example, if I look at the colors up here, red, blue, green, red, blue, green, red, blue, green from top to bottom. So that would mean a periodic or repeating pattern of properties. So here's a picture of Dimitri's first periodic table. So two things that I want you to notice are increasing atomic mass. So as I go from top to bottom, you should see that atomic mass is increased. So 50, 51, 52, 55. I see from top to bottom in the vertical columns increasing atomic mass. I also want you to take notice that as I go from left to right, elements that are in the same row have similar chemical properties. Another example. Fluorine, chlorine, bromine, iodine, they're all side by side, so all of these elements share similar chemical and physical properties. One last thing I want you to take a look at, I see question marks. I see a question mark there, I see another question mark here, and another question mark there. So just take a look. We see numbers next to the question mark. So this question mark has the number 68, and this question mark has the number 70, but there's no identity yet. Missing pieces. Mendeleev left numerous blank spaces as he was creating the periodic table. These were the question marks that we just circled on the previous slide. These are elements that had not been discovered yet, but that Mendeleev predicted existed just based on his table. In fact, eventually all of the missing elements were found, and they did indeed have the properties that Mendeleev predicted. Mendeleev did make a few changes. He broke the pattern of increasing atomic weight to keep similar reacting elements together. So if you remember from a few slides ago, we said that his table was organized by increasing atomic mass from top to bottom, and similar elements were together side by side from left to right. So he breaks his pattern of increasing atomic mass from top to bottom in order to keep elements that had similar properties right next to each other left to right. And if you look at the periodic table at iodine and tellurium, you'll notice that iodine has a mass of 126.9 and tellurium has an atomic mass of 127.6. But on Mendeleev's periodic table, he left them, or he switched them so that tellurium, Te, came before iodine. So even though iodine was heavier, he put it after tellurium on his periodic table. And he did this because he preferred to have elements that had similar properties right next to each other than having his pattern of increasing atomic mass from top to bottom. So now let's take a look at the modern periodic table. Before, we had increasing atomic mass from top to bottom in vertical columns and similar elements left to right, side by side. Along comes Henry Moseley, and he creates the modern periodic table, the one that we use today, the one that you have right in front of you. It's arranged by increasing atomic number, also known as the number of protons. So difference number one from Mendeleev's periodic table and Henry Moseley's periodic table is that now we have increasing atomic number instead of atomic mass. And most importantly, families or groups remain in vertical columns and retain similar properties. So essentially what we've done is we've taken Mendeleev's periodic table and we've flipped it. So where he had similar elements that were side by side, we now have, this says, most importantly, families or groups remain in vertical columns and retain similar properties. So we've taken Mendeleev's elements that were side by side, and now we've created a family, or we call them groups, from top to bottom. These elements have the same number of valence electrons. We identified these group numbers last week. So group 1A has 1 valence electron, group 3A has 3 valence electrons, and they all form the same types of ions. So modern periodic table is arranged by increasing atomic number. If you didn't write this down before on your periodic table, let's write down Henry Moseley's name. And let's put arranged by increasing atomic number. And families or groups are in vertical columns with similar properties. So periodic law, what we're studying right now, is the common change in properties as we move from group to group. So remember before we had similar elements that were side by side. So we had something like all reds side by side. Then we had all greens side by side. But now, based on Henry Moseley's periodic table, we flipped it. So now vertical columns are the same. So we'll get rid of this, and now vertical columns are the same. So red, and now green. It's my best of drawing a straight line. And let's say even purple. So now when we read the periodic table left to right, we get a periodic pattern in those physical and chemical properties. I'll just sum up those physical and chemical properties as colors. So now when we read the pattern from left to right, red, green, blue, purple. Red, green, blue, purple. So whereas before all the reds were left to right, now all of the reds are top to bottom. So when I read, just like I'm reading a book or reading words in a sentence and I read left to right, those properties will repeat in a pattern. And we call that a periodic pattern and physical and chemical properties. It allows us to use general patterns to understand properties of most elements without having to memorize each one. So for example, if you look at group 1A and all of the elements listed there, you have H, Li, Na, K, Rb, Cs, Fr. Instead of having to memorize the properties of every single one of those elements, because they're all in the same family, I'll just go and call those the red family, they all share similar chemical and physical properties. And it's because of that one valence electron. So they all behave the same way Most of them all look fairly similar to one another, and it just allows us to understand properties and to memorize the properties of a single group as opposed to memorizing specifics about each one of those individual elements. So it makes learning about elements and the periodic table much easier. All right, now flip to the front. We're going to label a few things on our periodic table. The first thing we're going to label are periods. From left to right, one row is called a period. I don't really care which one you choose, but I want you to choose a period from left to right, maybe highlight it or put a box around it, and I want you to label left to right as a period. Horizontal rows are periods on the periodic table. I also want you to take a look at the numbers on the far left-hand side. I'm going to highlight them all for you. These numbers right here are your period numbers. They also tell you the number of energy levels around your nucleus. So period number 1, all of those elements from left to right have 1 energy level. Period number 2, let me erase that because that's a little bit messy. Period number 2 here, all of the elements in period number 2 have 2 energy levels around them. Period number 3, all of these elements have 3 energy levels around them, so on and so forth. The next thing we're going to identify on our periodic table are vertical columns. We call vertical columns groups or families. So grab yourself a group, fill it in, and label it. Call this a group. We call them groups or families because typically people that are in families have similar physical characteristics, and the same is true for families on the periodic table. So I want you to take a moment, and it says each family is identified by a number and a letter. So on your periodic table you should see 1A, and then I'm trying to write it as small as possible. Then you see 2A. We're going to skip the transition metals for now. We'll come back to them. 3A, all the way down until we get to 8A down here. Make sure you have those labeled or even highlighted as your group numbers. Now, another important thing about the group number for our representative elements, so groups 1A through 8A that you already have highlighted or labeled, is that the group number represents the number of valence electrons. So group number 5A, for example, right here, all of these elements from here down have 5 valence electrons. All group 2A elements have 2 valence electrons. All group 8A elements have 8 valence electrons. Now the ones you see in the middle, I marked them out, your transition metals. Oops, that's not what I wanted to do. My transition metals, we call these non-representative elements. And you'll notice on your periodic table, they start over here with 3B and 4B, 5B. So they follow a pattern in terms of numbers, but they have the letter B. So the number on top of these groups does not represent number of valence electrons. We'll talk about transition metals in a few minutes, but I want to make sure that you're clear on both. So representative elements 1A through 8A, their group number represents their number of valence electrons. Non-representative elements are these found right here in the middle. These are your transition metals. Their group number does not represent their valence number of electrons. All right, we're going to flip to the back again, and you're going to create a T-chart on the back of your periodic table so that we can sort out the 3 major classes of elements found on the periodic table. So you're creating this T-chart that you see here. It has 3 different sections. The first section is going to be called metals, the second section non-metals, and the last section metalloids. Under metals, I want you to fill in the properties you see on the left. They're shiny, they're conductors of electricity, they're ductile or malleable, meaning they can bend without breaking, they form positive ions, they lose electrons, they're found on the left side of the periodic table. Most of them are hard or solid at room temperature. It may take you a little bit longer than it takes me to read, but make sure that you have all of these properties listed for metals. If you have to, pause the video so that you can copy all of these down. For nonmetals, typically they're the opposite of metals. They are dull, poor conductors of electricity. They're great insulators. They form negative ions. They're found on the right side of the periodic table, and most of them are gases at room temperature. One exists as a liquid, that's bromine, and one exists as a solid, it's iodine. Metalloids on the far right-hand side. They have some properties of metals and some properties of non-metals. These are typically found on that little staircase line that you see in bold on the front of your periodic table. If they are on the left side of that staircase, they typically have more properties of metals. If they're on the right side of the staircase, they behave more like non-metals. So like I said before, if you need more time to copy down these properties, just press pause before continuing on to the next slide. And last, right underneath your T-chart that you've just created, we're going to list a few special families. We have 1, 2, 3, 4, 5. We have 5 special families that we are going to quickly write about. So leave yourself enough space to write about all 5. The first that we're going to write down are alkali metals. So I want you to write the name alkali metals. We're going to list a few important properties about them, and then you're going to identify them on your periodic table. Alkali metals are group 1A, or group 1 metals. They are the most reactive metal family on the periodic table. They have 1 valence electron. They form positive 1 ions. And their oxidation number is +1. So take a moment, make sure you have all of these properties written down. Now flip to the front of your periodic table, and I want you to highlight or put a box around the group 1 metals. So the group that you see highlighted on this picture here is perfect. You can actually include hydrogen in there. It's not actually a metal at all, but it shares all of the same properties of these group 1 metals. So I want you to outline them and label them as alkali metals on the front of your periodic table. Again, if you need more time to copy any of these properties down, just press pause. The next special family we have are called the alkaline earth metals. They are your group 2A or group 2 metals. They're highly reactive, just like your group 1 alkali metals, but they're not as reactive. They have 2 valence electrons, so they lose 2 electrons to form positive 2 ions. Their oxidation number is a +2. I want you to flip to the front of your periodic table once you are done jotting down the important properties of alkaline earth metals, and I want you to color code your alkaline earth metals. Make sure you label them as well. Some students have trouble differentiating between group 1 alkali metals and group 2 alkaline earth metals, so here's my trick. Alkali, 1 word, group 1. Alkaline earth, 2 words, group 2. Then I want you to try to come up with some ideas for why alkali metals, which have 1 valence electron, are more reactive than alkaline earth metals that have 2 valence electrons. Come up with a good idea and then we'll discuss in class. Reactivity comparison. So I asked you to come up with some ideas for why group 1 alkali metals are more reactive than group 2 alkaline earth metals. We have 2 videos here, one on the left for potassium, which is a group 1 metal, and water, and one on the right for calcium, which is a group 2 alkaline earth metal and water. Now unfortunately I can't get the videos to play when I do the audio notes, but you can look at the picture and we can draw some conclusions here. So our claim is that alkali metals, that's your group 1 metals, that's potassium here, are more reactive than alkaline earth metals, which is calcium here, or group 2. By looking at the picture, take a look on the left at potassium. What kind of evidence do you see in just the picture alone that alkali metals are more reactive than alkaline earth metals? Give me a quick second. If you said fire, you would be correct. So alkali metals combust. They actually give off a ton of heat when they are added to water. Now on the right, it does look like there's a reaction occurring, but I don't really see a flame or any color, any combustion going on. So my evidence is that alkali metals, when they're added to water, they completely combust. Some even pop or explode, and we'll see an actual example in class together. On the right, that calcium, it does bubble, it gives off some heat, but it doesn't give off nearly as much heat as what you would see from the potassium. Our reasoning. So here's where that reasoning comes in. Why are group 1 metals so much more reactive than group 2 metals? And the answer lies in your number of valence electrons. Because my group 1 metals only have to lose 1 electron, they require much less energy to react, and they react much more readily. Calcium, on the other hand, has 2 valence electrons. Because it has to lose 2 valence electrons, remember that nucleus is holding those electrons in. So if you think about the amount of energy needed to remove 2 electrons versus the amount of energy needed to remove 1 electron, because it's less energy to remove 1, alkali metals are much more reactive than alkaline earth metals. Now back to our special families. We are going to add transition and inner earth or rare earth metals as a special family to your periodic table. We're on the back first, where we're identifying special characteristics. These are your group 3 through 12b. They're all metals, but they're not nearly as reactive as group 1 or group 2 metals. The important thing that I want you to write down about transition metals, and this is the reason why they don't follow the trend of group number and valence electrons, is that they form more than one oxidation state. We haven't really talked about oxidation state, but what that means is the charge that these metals would have if they were to lose electrons. So because metals lose electrons instead of gain electrons, they all end up with a positive charge. So transition metals, they get more than one option for what their remaining charge would be. So they can lose 1 electron, sometimes they can lose 2, 3, some transition metals can even lose up to 7 electrons. Now these transition and inner transition or rare earth metals, they're still shiny, they still conduct electricity, they're still ductile and malleable. The biggest difference between transition metals and alkaline earth metals is just their reactivity. So they're not as reactive and they form more than one oxidation state. Once you've copied down their characteristics, make sure you turn to the front, you color code your transition metals, and you label them appropriately. Our second to last special family are called the halogens. These are our group 7 elements, so these are on the far right-hand side, second to last group. They are very reactive, volatile, diatomic nonmetals. They're always found combined with other elements in nature, so they're like your one friend that can never be single. They are always found chemically combined to either another of the same element, so fluorine, for example. It is at the very top of group 7. Fluorine never exists all by itself as just one fluorine atom. It exists as 2 fluorine atoms chemically combined, or as fluorine with nearly any other element on the left-hand side of the periodic table. All of the halogens have 7 valence electrons, and they gain 1 valence electron to form a -1 ion. Their oxidation state is a -1. So remember before, oxidation number is the charge an atom will have once it gains or loses electrons. Well, our halogens, because they already have 7 valence electrons, in order to complete their energy level, so if you count how many spots do my halogens need to go from group 7 to group 8 over here to have a complete energy level, they only need 1 more spot to fill. And that's just 1 more electron. So by gaining 1 valence electron, they have 1 more electron than protons, and they'll end up with a -1 charge. Make sure you turn to the front of your periodic table, you highlight or color code group 7, and you label them as halogens. Noble or inert gases are the last special family. On the back of your periodic table, make a quick list of characteristics of noble gases. They are group 8A or 18. They're non-reactive, stable, have 8 valence electrons, and no oxidation state since they neither gain or lose electrons. Flip to the front, highlight the very last group on your periodic table, and label them as noble gases. And the very last thing that we'll do today is we'll label oxidation numbers. They're going to come in very handy as we go through the atomic bonding unit coming up next. At the very top of each group, you're going to write the following numbers. +1 for all of group 1. Because all of group 1 elements lose 1 valence electron, they will always have 1 less electron than proton. Because they have 1 less negative charge, they will end up with a +1 charge. On top of group 2, a +2. Skip the transition metals, remember they have more than 1 oxidation state, and then move over to the top of group 3, add a +3. I'm going to do an example with you very quickly. I'm going to choose aluminum. Aluminum has 13 protons and 13 electrons. But if aluminum loses 3 electrons, it now only has 10. If you analyze number of positive charges versus number of negative charges, aluminum will end up with a positive 3 charge, and that's where that oxidation number comes from. On top of group 4, we're actually not going to give them any oxidation numbers. If you really feel like it, you can put a plus or a minus 4. It would actually do both. And then on top of group 5, you'll put a negative 3. On top of group 6, a negative 2. Your halogens get a negative 1. And noble gases, since they neither gain or lose, they don't get an oxidation number.